Hi everyone, this is Professor M. Does Science, and today we're going to discuss the energy eigenvalues of the hydrogen atom in another one of our videos on rigorous quantum mechanics. The hydrogen atom is made of a proton bound to an electron. The states of bound systems are associated with a spectrum of discrete or quantized energy eigenvalues. In this video, we will start from the mathematical definition of those energy eigenvalues, which we have derived in one of the videos that are linked in the description, and we will find out that energy eigenvalues are actually highly degenerate. We will discuss the symmetries that give rise to these degeneracies, and we will also introduce some widely used notation that you've probably encountered before if you've studied atomic physics or chemistry. We're talking about atomic shells and subshells, of course, and we're also going to introduce the concept of spectroscopic notation. So let's go! The hydrogen atom is made of a proton and an electron. In the introductory video on hydrogen, we find that the relevant physics of the system is encoded by the relative motion of the proton and the electron. And that means that we can describe the hydrogen atom with a one-particle relative Hamiltonian H, which has the usual kinetic energy term, and this potential energy term that's associated with the Coulomb interaction. In the position representation, we can rewrite it with the usual kinetic energy term and the potential energy term, which has the form of a central potential. And for a full derivation, you should check out the introductory video on the hydrogen atom, but as a reminder, mu right here is the reduced mass of the system and is related to the masses of the proton and the electron by this equation. P here is the relative momentum, given by this expression in terms of the individual momenta of the proton and the electron, and R is the relative position, given by the distance between the proton and the electron. Starting with this relative Hamiltonian, we can write its eigenvalue equation like this, where as usual, these are the eigenvalues and these are the eigenfunctions. We have three quantum numbers labeling the eigenvalues and eigenfunctions, and they are k, l, and ml. The label k appears in both eigenvalues and eigenstates, and it can take any positive integer value. This quantum number is directly associated with the Hamiltonian eigenvalue equation and labels the different eigenvalues. The label L also appears in both eigenvalues and eigenstates, and it can take any non-negative integer value. It is associated with the square orbital angular momentum, and the hydrogen atom eigenstates are labelled by L because the operator L squared commutes with the Hamiltonian, and this means that we can choose the energy eigenfunctions to also be eigenfunctions of L squared. Finally, the label ml only appears in the eigenstates, and for a given L, it can be -L, -L plus 1, and so on in steps of 1 all the way to L. ml is associated with the z component of orbital angular momentum, and the hydrogen atom eigenstates are labelled by ml because the operator Lz commutes with the Hamiltonian, and we can choose the energy eigenfunctions to obey this eigenvalue equation. We've solved this eigenvalue equation at the top to determine all the bound states of the hydrogen atom in a series of rather mathematical videos that is linked in the description. What we want to do today is to take a closer look at the eigenvalues, which will allow us to expand our understanding of the hydrogen atom. Right, so from our earlier videos on hydrogen, we know that the solution of the eigenvalue equation of the Hamiltonian leads to a discrete energy spectrum for the bound state of the hydrogen atom, which is given by minus the ionization energy divided by k plus L squared. Remember also that the ionization energy EI is given by this expression in terms of the reduced mass mu and a number of fundamental constants, and that its numerical value is 13.6 electron volts, and that's the kind of number that you probably want to remember. Additionally, remember that k can only take positive integer values and that L can only take non-negative integer values. Looking at the eigenvalue equation at the top, we see that the eigenstates are labelled by an additional quantum number ml, which does not appear in the eigenvalues. Remembering that for a given L, the possible values of ml are -L, -L plus 1, and so on in steps of 1 all the way to L, then we can conclude that for every L, there are 2L plus 1 distinct values of ml. In turn, this means that the energy eigenvalue EKL is at least 2L plus 1-fold degenerate. To put it another way, the eigenvalue EKL has at least a degree of degeneracy, which we will call GL, and which is equal to 2L plus 1. This degeneracy is a direct consequence of rotational invariance. The orbital angular momentum operators commute with the Hamiltonian, and therefore angular momentum is a conserved quantity in the hydrogen atom. But it turns out that there are even more degeneracies. Note that the eigenvalues EKL don't separately depend on K and L. Instead, they depend on the sum K plus L. And this means that if we have a pair of K and L, and a generally different pair K prime and L prime, as long as their sum is the same, then the energy eigenvalues are also the same. What does that mean? That means that energy eigenvalues can also be degenerate even if they have different L labels. Just like the 2L plus 1 degeneracy associated with EKL arises from rotational asymmetry, this additional degeneracy that we've just seen when the sum of KL equals that of K prime plus L prime also arises from another symmetry of the hydrogen atom. This extra symmetry is a little bit more subtle, and I will only say a few words here. Classically, this symmetry is present in any potential that arises from an inverse square law, examples including Coulomb's law of electrostatics and Newton's law of universal gravitation. All these potentials conserve what is called the Runge-Lenz vector, and in the case of the Coulomb law, it is given by a term involving the cross product of the linear momentum P and the angular momentum L, and a term involving the position vector R. The extension of this Runge-Lenz vector to quantum mechanics also leads to a corresponding conserved quantity, and that in turn leads to this additional symmetry that we've just found in the hydrogen atom. So we found that there are plenty of degeneracies in the energy spectrum of the hydrogen atom. To put some concrete values to these degeneracies, it will prove convenient to first introduce a new label. We can group the K and L labels appearing in this sum and define a new collective label N. With this new notation, we can write the eigenvalues as En and set them equal to minus the ionization energy over N squared. Given the possible values of K and of L, we can conclude that N, which is the sum of K plus L, can only take positive integer values. And from the definition of N here, we can also conclude that for a given N, then L can take any value from 0, 1, 2, and so on in steps of 1 all the way to N minus 1. With this new label, we can now rewrite the energy eigenvalue equation of the hydrogen atom like this. The energy eigenfunctions depend on 3 labels, N, L, and Ml, but the energy eigenvalues only depend on the label N. So, what is the total degeneracy of an energy eigenvalue En? To answer that question, first remember that for a given L, we have a degeneracy GL equal to 2L plus 1 corresponding to the possible ml values. For the full degeneracy of En, we're going to use Gn. As we can see up here, for every n, L can run from 0 to n minus 1, which means that Gn is equal to the sum from 0 to n minus 1 of GL. Using this expression for GL and inserting into our expression, we can rewrite Gn as equal to this sum of 2L plus 1. This is a standard arithmetic series, and the sum evaluates to n squared. And that's it. The energy eigenvalue En of the hydrogen atom has a degeneracy equal to n squared. This degeneracy arises from a combination of rotational symmetry and also from the conservation of the quantum mechanical version of the Runge-Lenz vector. It's important to add a small clarification to this result. We're working with the non-relativistic Hamiltonian of the hydrogen atom. If we considered electron spin, then the degeneracies we found would actually double. And if we considered additional relativistic corrections, then some of these degeneracies would actually be lifted. But more on that in the videos linked in the description. Right, before we move on, we should introduce some widely used notation that will be convenient. When working with the hydrogen atom, the quantum numbers that you will encounter most frequently are N, L, and ML. These quantum numbers are used so often that they have special names. N is called the principal quantum number. L is called the azimuthal quantum number. And ML is called the magnetic quantum number. The name for ML may appear somewhat arbitrary at this point, but its origin is in the fact that the energy eigenvalues are degenerate in ML unless there is a magnetic field. Ta-da! In the rest of the video, we'll introduce some additional widely used notation to describe the hydrogen atom. To do so, it will prove convenient to first plot the energy eigenvalues. So let's draw a vertical axis, which corresponds to the energy, and we're also going to draw a horizontal line to set the zero of energy. As we're discussing bound states of the hydrogen atom, all energies are negative, and therefore we are going to draw them below this horizontal line. So let's start with the ground state n equals 1. The energy is simply minus the ionization energy, which has a value of, remember, minus 13.6 electron volts. And remember also that for n equals 1, the only possible value for the azimuthal quantum number is L equals 0. So how do we plot this in the diagram? We're going to draw this energy eigenvalue as a short horizontal line at the corresponding energy. We're now going to label this level with its principal quantum number, n equals 1, and also with its azimuthal quantum number, L equals 0. Let's make some room. And let's now move on to the first excited state, n equals 2. The energy is equal to minus the ionization energy over 4, which has a numerical value of minus 3.4 electron volts. For n equals 2, we have two possible values for the azimuthal quantum number, L equals 0 and 1. Going to the diagram, the energy will be here. And we're now going to draw this energy eigenvalue with two horizontal lines. The first is right above the one for the ground state, and we're going to draw another one to its right here. Both correspond to the principal quantum number n equals 2 and have the same value. However, we are separating the two possible azimuthal quantum numbers with the first line here labelled by the L equals 0 down here, and we will add a new label L equals 1 for the second line. Now, both lines correspond to the same energy. We're simply separating them according to the azimuthal quantum number for convenience, and the reason why will become clear a bit later on. Let's make some room again. And we will now consider the second excited state, n equals 3. The energy is equal to minus the ionization energy over 9, which has a numerical value of about minus 1.5 electron volts. For n equals 3, we have 3 possible values for the azimuthal quantum number, and that is L equals 0, 1, and 2. Going to the diagram, the energy will be here, but we won't explicitly write it so that we don't clutter the diagram. We're now going to draw this energy eigenvalue with 3 horizontal lines. The first is right above the L equals 0 lines for the ground and first excited states. The second is right above the L equals 1 line for the first excited state. And we will draw the third to the right here. All 3 lines correspond to the principal quantum number n equals 3 and have the same value. We're again separating them by their azimuthal quantum numbers, with the first line labelled by the L equals 0 down here, the second by L equals 1, and we add a new label L equals 2 for the third line. And let's make some room again. We now consider the third excited state, n equals 4. The energy is equal to minus the ionization energy over 16, which has a numerical value of minus 0.9 eV. For n equals 4, we have 4 possible values for the azimuthal quantum number, L equals 0, 1, 2, and 3. So going to the diagram, the energy will be here, and we're now going to draw these 4 horizontal lines. All lines correspond to the principal quantum number n equals 4 and have the same value. We are again separating them by their azimuthal quantum numbers labelled by L equals 0, L equals 1, L equals 2, and we add the L equals 3 label down here. We could of course go on like this forever and ever and ever for higher excited states, but by now hopefully you've seen how it works. So let's make some room once more just for clarity. This depiction of the energy spectrum of hydrogen is a widely used one that you may have actually encountered already. While it may appear somewhat strange that we are explicitly separating the degenerate eigenvalues according to their L quantum numbers, but saying nothing about the ML quantum numbers, this depiction allows us to introduce some important notation that is used in atomic physics. The first concept that we introduce is that of an atomic shell, and you may have heard that term before. All states associated with a given principal quantum number n form an atomic shell. That means that all energy levels for n equals 1 form the first shell, all energy levels for n equals 2 form the second shell, and so on. The second concept that we want to introduce today is that of an atomic subshell. We divide all states in a given atomic shell into subshells, and each subshell is labelled by a given azimuthal quantum number L. So, the n equals 1 shell has a single subshell, that's right here. The n equals 2 shell has 2 subshells. The first corresponds to L equals 0, and the second to L equals 1, and so on. And while we've introduced these concepts in the context of the hydrogen atom, this nomenclature is actually widely used for other atoms too. So you may have encountered it before if you've studied atomic physics or chemistry. Okay, one more exciting thing before we finish. We're going to introduce the so-called spectroscopic notation. Spectroscopy refers to the study of the electromagnetic radiation that results from the interaction between light and matter. Historically, spectroscopy plays a key role in the development of atomic physics, often preceding formal understanding of the quantum mechanics. For the hydrogen atom or any other atom, if the system is in an excited state, it can transition to a lower energy state by the emission of a photon. And in spectroscopy, these emitted photons are detected and interpreted. I would recommend that you take a look at our video on the hydrogen spectral series, where we discuss this in more detail. But for our purposes today, all we need to know is that the spectroscopic notation we will now introduce has its origins in the study of photons emitted by atoms when relaxing from high to low energy states. Before quantum mechanics, the various atomic spectral lines observed in spectroscopy experiments were given names according to their general features. We now understand these different features as arising from the different azimuthal quantum numbers. So, the L0 states are described by the letter S, and it comes from the word sharp to describe the observed spectral lines. The L equals 1 states are described by the letter P, and it comes from the word principal, and note actually that this name has no relation to the principal quantum number. The L equals 2 states are described by the letter D, and this label comes from the word diffuse, which again refers to the features of the spectral lines that are observed experimentally. The L equals 3 states are described by the letter F, and the label comes from the word fundamental. And all subsequent entries are followed alphabetically. So L equals 4 would be G, L equals 5 would be H, and so on. Fun fact, the letter J is actually omitted because it can be confused with the letter I. But for most applications, you will never really need to go beyond the F label anyway. We can now go back to our diagram and relabel it using spectroscopic notation. The L0 states are the S states, and this means that these are the 1s states, these are the 2s states, these are the 3s states, and these are the 4s states. The L equals 1 states are the P states. There are no 1p states, and we first have the 2p states, then the 3p states, the 4p states, and so on. And the L equals 2 states are the D states, which start at 3D. And in this diagram, we also have 4D. And finally, the L equals 3 states are the F states. And in this diagram, we only have the 4F states. Many of the ideas that we've introduced today can be generalized to all other atoms. So if you go on to study atomic physics or chemistry, you will often find yourself talking about atomic shells or subshells, as well as S, P, or D states. So that's all for today, and as always, if you liked the video, please subscribe.